talk. And Ricardo, the floor is yours.
Okay, thank you, Anna, for this kind introduction. I will move ahead for the talk. So our talk today is titled The Cognitive Systems Toolkit, CST, and the Hub for Artificial Intelligence and Cognitive Architectures. Well, I will talk just a little bit about the Hub. A Hub is a very interesting initiative that we have at Unicamp, congregating professors from many different kinds of themes. So right now we are structured into 5 main themes. One theme which is learning in cognitive architectures, and I have some pictures of the main people working on each part of these themes. The second one is cognitive architectures. The third one is to device edge cloud model training, knowledge representation, and natural language processing. The Hub is an initiative that is sponsored by leading companies in mobile systems. And the idea is to understand how we can use cognitive systems in mobile devices. And so we have created all these different themes for working this whole idea. Okay. I will talk very little bit about a cognitive agent, the idea of cognitive agent that we have for ourselves. For us, a cognitive agent is a kind of intelligent agent that is being controlled by a cognitive architecture, and this is our main interest in talking about a cognitive architecture. And what is a cognitive architecture? More than a computational architecture that gets some information from cognitive science and cognitive psychology, and we try to inspire ourselves to create new kinds of technologies to achieve some kind of possible cognition from these agents, turning them into intelligent agents. Okay, so for us, a cognitive agent might use different intelligent systems, techniques, and algorithms, and this is the main idea that we have for a cognitive architecture. Well, what is the difference between a cognitive architecture and other kinds of architectures? The idea is that in a cognitive architecture, we can mix together those very different kinds of techniques. So we are talking about neural networks, fuzzy systems, evolutionary computation, swarm intelligence, whatever you think, and we want to combine them together in an architectural way such that it can perform these cognitive functions that we expect them to exhibit. Okay, so for us, these cognitive agents might execute synchronous or asynchronous online processes and might have some kind of learning or not. So depending on the situation, we will be having learning. In other situations, we don't have learning. And here on the right, we have a kind of an example of what could be something like this. So we have these elements with these boxes with 4 small boxes around that we are calling codelets, and we have these circular nodes that we are calling memory objects. I will talk about them later. And in some way, we are combining these things in some architectural way such that it can provide a kind of a cognitive functioning for the agent. Okay, so let's go into the basics of our CST, the Cognitive Systems Toolkit. This toolkit was at the first, it was before the creation of the Hub. It was a project from FAPESP, which is the São Paulo State Foundation for Scientific Development. And we started this project many years ago, and the idea was to create the main infrastructure for building cognitive architectures in a very general way. Because if you go to the literature, you see that we have more than 200 cognitive architectures available in the literature, and each of them, in some sense, are fixed or framed into a context that if you use it, you cannot mix with other techniques. And the whole idea behind CST was that we would like to have a toolkit that we could build a cognitive architecture very easily and without having to have strong commitments with such and such kind of technique. So you'd like to, oh, I want to use, for example, a behavior network. Oh, I don't want to use a behavior network. I can move, and then I can combine things together such that we can build this architecture in such a way that we can try different kinds of technologies and see how they work together and build a kind of cognitive function for us. Okay, so the main idea behind CST is that we have two kinds of assets. The first one is the codelet. And what is the codelet? We didn't invent this name codelet. Codelets is an idea coming from Hofstadter, which was used, for example, in the LIDA cognitive architecture from Stan Franklin and others. But we used this, we borrowed this idea of a codelet as a kind of process that keeps repeating, calling the same small amount of code in an iterative way and periodic way. So the main idea behind a codelet is that we have a fragment of code that is being called repeatedly over time. Okay, this codelet has two input parts: the local input part, where we are going to connect this codelet with memory objects, okay? And we have also a global input part that is used for a broadcast mechanism that is used in a kind of consciousness model from Bernard Bars. And so we have this global input also that comes from this broadcast mechanism. And these two parts are going to enter data into the codelet. The codelet will be calling this, this procedure proc repeatedly, iteratively over time, okay? And then we have an output that is going to be directed to a memory object, okay? We also have some kind of activation, and this activation is also being set up by this proc procedure. And the idea is that this activation is using for this global workspace theory that is used behind consciousness, so we can have this mechanism of consciousness also using CST, okay? The idea is that these codelets, they are within a code rack where we are structuring them, okay? And then using these local inputs and outputs, we are going to have influence. So for example, this codelet is directing some information to this memory object that is going to send information from this codelet that going to this memory object and then to this codelet, and then we have a coalition. We can have coalitions that are fixed or just like a neural network, we are creating these connections prior to the architecture, but these coalitions can also form dynamically. I mean, these connections, they could be learned during the interaction of the codelets forming the architecture. And so we can have very interesting kinds of things forming with these coalitions. These coalitions are also important for the global workspace mechanism used for structuring consciousness, okay? Well, about memory objects. Memory objects are a kind of a wrapper or a container of some kind of information that is the I here, okay? We also have a timestamp that is going to assign and say, okay, this information was generated in this specific timestamp. And we also have some kind of evaluation which can be used for different purposes within the architecture. But this is what is encapsulated in this memory object. Okay, we also have this connection to semiotics, so this memory object can also be called a sign. Okay, then we can think of this same structure here. Okay, look at this code rack. Okay, now I'm going to put some thematic roles for each of these codelets. And then you can see that we still have here the code rack and I still have the raw memory, but now I have that some of these codelets will be performing some kind of cognitive function. So I will have sensory codelets, I might have perceptual codelets, attention codelets, emotional codelets, learning codelets, language codelets. I need some consciousness codelets too, imaging and planning codelets, behavioral codelets, and motor codelets. And also the memory, instead of having a complete raw memory, I will have some kind of thematic kinds of memories inside it. So I will have a sensory memory where I will be handling some kind of sensory memory objects, perceptual memory where I will be storing some kinds of categories and patterns and things like that, episodic memory where I will be storing episodes and things like that, semantic memory, procedural memory, motor memory, and also we have a working memory using Baddeley's idea of having a phonologic loop, a visual sketchpad, and episodic buffer. And besides all of this, we have consciousness. So consciousness can be in any kind of these memories, and the mechanism of consciousness is going to decide based on activity, which is most important to be promoted to consciousness. And then you have this broadcast of whatever is in consciousness to all the global inputs of all the codelets, and this is how the global workspace mechanism happens using CST. Okay. There are many background theories that we are using here. One of the most important of them is the dual process theory, the idea that we have two different kinds of systems in a cognitive architecture. The first one is type 1, and the second one is type 2. This idea is being fostered by many different researchers, and maybe a famous one is Kahneman in his Thinking Fast and Slow book, where he talks about it. And so this is one of the theories that we have in the background. Another one is Peter Gardenfor's geometry conceptual spaces, and specifically from this book, Geometry of Meaning, where he tries to make a connection between different kinds of words in a natural language and how you can have a geometric understanding for a kind of representation for these words. We also have a firm ground in semiotics, and talking about that, specifically about the Peircean semiotics, the semiotics of Charles Sanders Peirce. Just as a small introduction, we may use different kinds of representations, icons, indexes, and symbols. In some sense, we are connecting semiotics to the theory of grounded cognition from Barsalou. And so we have this idea of a model and model symbols, and we have this important idea of mental simulation, where we are making some kind of perceptual reconstruction in space and time of episodes, and we are using that also in CST. Okay. Another background theory is subsumption theory, but Brooks' subsumption idea, but also dynamic forms of subsumption. So we have this idea of dynamic subsumption, which is also an interesting background that we use in our architecture. The main node, or the main idea that we use in CST in terms of knowledge representation, is the idea of idea. So we have this as a formal part of CST. And the idea is something that has a name, that has a value. This value is any kind of object, because CST is made in Java. This can be whatever kind of Java object, but in most cases we use numbers, like float type or integer types, and symbols, strings. Okay, these are the most typical kinds of objects, but we can use any kind of object here. Okay. An interesting thing of the concept of idea is that ideas are connected to other ideas in some way. So one idea can have connections to many other ideas, and an idea also has a category which by itself is also an idea. So everything in CST are ideas, and we can change whatever kind of data that we have into ideas. So idea is the basic building a kind of knowledge representation on top of which we can build many other kinds of representation. For example, we can have different kinds of ideas. So the main kind of idea is that of an abstract object. So we can think of an object from the world. Okay, this object has properties, and this property has quality dimensions. And then if we, in some sense, look at this object on time, we will be able to create episodes, and then having multiple episodes from multiple abstract objects, we might have scenes, and we also might have affordances or ways in which we can act or operate on top of these abstract objects. So all of these kinds of things are also ideas, and they are represented as ideas inside the CST. Okay. Well, let's turn to some examples of the use of CST. We have worked in at least two, but some more kinds of examples of creating projects using CST. The first one was this cognitive manager for smart cities, a project called CMCA, funded by Ericsson Research together with the University of Campinas. The idea here is that we can have a topology of roads and streets in a city or a town, and we might have controlling important assets of this traffic situation. We can have different cognitive managers controlling, for example, the traffic lights, or controlling the position of a car, or having also it in fixed places. In this particular project, we have the Junction cognitive manager, which is controlling the traffic lights. We have the car cognitive manager, which is a smartphone application that is together inside the car, so the person that is driving the car. This car cognitive manager talks to the coordinator cognitive manager, and then the coordinator cognitive manager sends to the car cognitive manager the address for the closest junction cognitive manager, and then they can cooperate together in order for creating a situation in which we can have some kind of traffic control. Okay, so just for you to understand how difficult this can be, this is the model for a single junction. Okay, so we have lanes here, and from each of these lanes we can make some kind of conversions to the left, to the right, and so we need to have different kind of phases for the traffic lights such that it can control the junction. Okay, just for you to understand how this can be tricky, in this slide we have two different junctions, the west and east junction, and we can see that in the west junction we have 4 different phases for the traffic lights, and in the east junction we have 3 different phases, and so the junction controller needs to decide when is the proper time to move to the next phase. Okay, by enforcement of law, we need to follow this sequence, but we can have one of these very fast, so just a few seconds, for example, and then move to the second one, and this is the decision that the junction controller is doing. Okay, we have some input sensors for the system, an occupation sensor that tries to see how much cars are stopped into a lane in a red traffic light. We have the phase time, how much time has passed since the last change in the traffic lights. We have the number of vehicles in all the lanes. We have an average speed for the cars crossing the junction. And we also have some smart car info because we have this concept of smart cars. So a smart car is something like an ambulance or a firefighter or a police car that needs to have some sort of preference in the junction. And so the controller is going to provide this for the system. Okay. This is an example of the cognitive architecture that we created for controlling this problem of the cognitive manager. We can see here some detail on the different kinds of codelets that we have. Unfortunately, I don't have too much time to enter into these details. But if you have questions, we can come back and talk a little bit about how they work. Okay. The second example that I'm going to show you is the project Troca, which is also funded by Ericsson Research together with University of Campinas. And the main idea here is to have the transportation of packages in a factory or warehouse environment. We have created this using the VRAP simulator together with ROS, the robot operating system. And the main tasks in this project was package transportation, environmental exploration, performing some kind of warehouse inventory, making the energy management for the robot such that they can refuel its energy when it's necessary, dealing with human operators, dealing with other robots, and also some.
Ricardo, can you hear us? I think maybe the connection might have dropped for a moment.
Kind of self-monitoring.
Okay,
and
there we go.
Okay.
Okay,
May I
back.
proceed?
Yes, now we're back.
Okay.
Thank you.
Okay. And then here we have other slides showing the factory and the different kinds of processing stations that we have, and also the stores on the back. Okay, and here we are showing the packages and how we pick these packages. And here we have the cognitive architecture. Are you listening to me? Yes.
Yes. We hear you fine.
Okay. Here we have the cognitive architecture. We have also system 1 and system 2, and we have motivational systems. We have a behavioral system, activity system, subsystem. Here we have some details on each of these codelets. Unfortunately, I don't have time to enter into the details here, but we can turn back to it if it's necessary. And then I will move the word to Esther to talk a little bit about the other projects that we have using the CST mobile. Esther, please go ahead.
Thank you, Ricardo. Thank you all for watching us. I think the idea was to show to you that CST is a very broad framework and toolkit to work with either robotics or other kind of cognitive agents. And I think Letícia is going to show us a way to use also another way that we've been using CST. But lately, I think around 1 year ago, we've been approached by a major player in mobile devices, that is Motorola. And they decided that it was time to bring more intelligence to actually the mobile agents. And the idea was to foster the development of cognitive architectures for mobile devices. So CST, the hub of artificial intelligence and cognitive architectures, has been created with that goal. And CST was selected as our main tool because, as Ricardo mentioned, there are plenty of cognitive architectures in the literature and plenty of frameworks, but there is a lack of studies in the area related to mobile devices, and to seek for how we can relate what are the challenges to bring these cognitive architectures to mobile devices. So CST Mobile is our extension of it's an open project as CST, but is our extension of CST to work with Android operating systems, but that can also, the components are also being be able to be used in non-mobile architectures. So I'm just going to go a bit on CST Mobile, but the idea of CST Mobile is that we are facing many of the issues that we face when we are working with robots as well, because the first thing was like, which kind of cognitive architecture we are going to design. So we face some challenges, is how we can design it. Is there an architecture that fits us? And I will show you later the kind of way that we are working on, but what kind of sensors and actuators are fit for an agent that is built under a mobile phone. So a mobile phone is like in Brazil, we have actually, I think Brazil is one of the countries in the world that has more mobile phones, that people use mobile phones a lot. It's something around 1.5 mobile phones per person in our country. So it's a very powerful architecture, but tool. But literacy in Brazil is a problem as well. So if we have agents that can communicate better with the user, and if they can provide richer information and richer advices to the users, that will be a benefit as a whole. So the first thing that we had to think when we were talking about a mobile cognitive architecture was what kind of sensors, besides the traditional gyroscopes, EMU sensors, and so on, what we could use in a mobile phone that would make sense to learn with this agent or with this structure and be give good advices. So how can we validate this kind of mobile cognitive agents? Like, which kind of use case could you build? So these were like the first questions that arrived to us when we were first talking about building this CST Mobile. What kind of framework would support us? We know that there is still a gap in cognitive architectures between like the traditional cognitive agent approach and deep learning, for instance. So how could you take advantage of what we've been doing in specific applications in deep learning and bring them together and take advantage of these tools in our case? So what kind of framework could support this? What was necessary? That was another challenge for us. How to train these models, because we know that we have a limited amount of power. We can't spend all the battery from the mobile phone, otherwise we'll be like wasting our time doing what we are doing. So how can we distribute training and distribute learning, for instance? And that's why you've seen at the beginning that one of the areas that we research in the hub is distributed learning, federated learning. So we are and privacy is an issue for us. So we can't send the data from the user outside of the device and not guarantee that it's being treated correctly. So we have a real group researching, a big group researching on federated learning. So we can train our models in an efficient way, but also in a secure way. The other thing that we think that is an issue in most of the cognitive architectures and agents is how we can see, how can we visualize what the agents might look like. So if I have like a simulation model and I can see that there is a user walking around the campus of our university and is behaving like in a certain way, And then we are deriving like a set of episodes from that, how we could visualize that in the sense that we are seeing what the agent mind is building. So we decided to give a lot of efforts, put a lot of efforts in terms of visualization as well, and how we could address this gap between deep learning, as I've mentioned before, and the cognitive agents. And that's why we have another area that is concerned with knowledge representation is how to address the numeric to symbolic problem. So we know that this is an issue in the literature right now. So in a very general way, the core idea of the framework that we've built around CST Mobile is that CST Mobile runs inside core written in Java, is working inside the mobile phone, but is through endpoints, it's able to communicate with other architectures like SOAR, JSOAR, with deep learning, deep reinforcement learning frameworks, for instance. So we are building specific environments to work with cognitive architectures inside CST and outside. So we can use like the state-of-the-art in deep reinforcement learning along with the cognitive agent built in CST Mobile. But we are also able to visualize what is going on in the mind, the agent's mind, by having a visualization tool. And all of this is working together with the mobile phone, either to control the mobile phone or to gather data. And these sensors are not just sensors from like traditional sensors, but we also have applications and data from the user profile. So there are plenty of applications that are available. We try to be as not invasive as possible. So we don't use usually microphone, we don't use the agent, the user's camera, we don't go inside their applications, but we profile them to see what is your, like, what kind of application do you use more? What you are more interested to. So the idea is that we've selected a list of applications that could work for us as sensors. And we created this virtual sensor environment that can provide us this information so we can make our agents decide what is best to do. Gudwin, I think you can move. So this is like the first draft of our visualization tool. It's an HTML written mind viewer. And the idea is that we can see actually everything that is inside the agent's mind. We can see like an attentional map that's being created and see what is getting the agent's attention right now. We can visualize each codelet, how each codelet is processing a long time, either from online or offline data. It is communicated with the agent using REST and gRPC, so we can run this outside the mobile. And our idea is that the mind viewer is extendable to CST, so it's not for CST Mobile. And it's now we are starting to build what we call an ego-centered view of the agent. So the idea is that if you are running around the campus and we are building this episode, I could see this in a visualization tool that is a 3D model of what is going on in the environment. So, Ricardo, I think we... And to do all of this, we've created some use cases. So for instance, for energy optimization and for the agent's well-being. So we want to give advices to the agent in such a way that we are going to consume less energy. And at the same time, we are going to provide the best to act in the mobile in such a way that we are going to customize the mobile without need for the user to do it by itself. So you don't have to go there in your brightness configuration and configure how you want your brightness level. You don't have to go there and put your mobile phone, for instance. You wouldn't have, if everything is working well, you wouldn't have to go there and say, okay, I'm going to class right now, so I should turn off the volume of my mobile phone. The mobile would have to understand this, using this information, this profile of the user and the context around it, and make these decisions. And this is learned to each user. The idea is that, so we have all the challenges of how to use prior knowledge, do incremental learning, and use these memories to create the profile of the agent a long time, and so on. And this is just a sketch of one of the first drafts that we did for the cognitive architecture for this use case. So we have a lot of sensors. We are working right now on building a episode tracker of the user, so we can create episodes in the memory, and from that we have a motivation system, and we have attention working on that. So we have all these cognitive elements working together to provide the best action possible. So it's just using CST. So you see that is all modeled using CST, and some of these components that are independently of the cognitive architecture that we are using. So if you want to reuse the attention components, bottom up or top down, if you want to use the motivation based components, you can use it. But when we put all together, we have like the use case that, or the cognitive agent that we are building our goal. So I'm with it. So I think the last example that what we want to do is like, we want to learn with the agent. So we want to like take the sensors and see that I have like a user entering a church, and then to see that this user has just turned down the phone or the volume. And then by seeing these sparse events, they don't have to be dense events. They are probably going to be sparse events. We want to learn that whenever I get to a classroom, for example, if I am a student, the cognitive agent would have to make a decision that is similar to that, because a classroom is not a place for noise. So you should be able to select this action by itself. So, and it's important to remember that these decisions, they do require a lot of context and information, because if I am, for instance, touristing around France, I don't want actually to turn down the phone because I'm outside the church. I'm close to a church, but I'm not actually inside the church. So there is no need for that. So the decision is different, and all these decisions changes if I am the professor, if I am the student, if I am the priest, for instance, inside church. So the idea is that this customizable cognitive agent is learning with the system all the time to make the best decisions possible. So this is how we're working on, and you've seen that we have like natural language processing also issues to help us describe the scenes and to create these long-term memories that can help us understand how this user works and how we should help them. And the idea is that we have a use case now for battery consumption, but battery consumption is just a way that we can measure very strictly how things are going. But that's not the ultimate goal of the project. So we are around 70 researchers right now, and these are going to, we are just extending the project to around 100 between like postdocs and PhD, master's students, and so on. And the code will be, everything that we are doing will be available online and open source. And the idea is that this architecture could be, all this framework could be used not only for mobile phones, but also for other kind of similar agents that will need the same kind of thing that we are doing. So I think that's the idea behind, just to give you a broad review of CST and CST Mobile. Thank you.
Thank you very much. Thank you, Ricardo. Thank you, Esther. So if we have, we can take now 5 minutes for questions before continuing with Leticia's presentation. If you have any questions, you can raise the hand and I can unmute you, or you can write in the chat if you prefer. While we wait, I have a lot of questions, but I will start off with one. So Esther, in the presentation for CST Mobile, you mentioned that also it interacts with JSOAR, so with the Java version of SOAR. Can you tell us a bit more about how the two cognitive architectures interact between each other?
Yeah, I think Gudwin can answer if you want. Yeah.
Well, the whole idea is that at the beginning, we didn't have no kinds of planning capabilities in our main codelets. And we have a SOAR that could do planning for us. And so we started to create some codelets to make the binding of a CST to JSOAR. So the idea is that we can prepare the information, and then we can turn our ideas into SOAR's working memory elements. And then we give control to SOAR, and SOAR makes the plan, for example, and gives us the plan back. And then we can use this plan together with other components in CST. So the interesting thing is that we can use everything that is already in JSOAR, for example, but we can bind it to other kinds of techniques that are not built in JSOAR. For example, we can do pattern matching, we can use learning, we can do whatever you want, and then we can put this together with JSOAR, for example, and we can have a more complete and more bigger kind of cognitive architecture that uses JSOAR together with other kinds of components that could be useful.
Thank you. Do we have anyone?
Yes, I have a question. Thanks a lot. This is really very interesting. I have a question about the codelets. How I imagine that they are not that they are reused in different coalitions, and I wonder how you handle this, the dynamics of the process. Which, yeah, otherwise I have a look, otherwise it looks like everything is frozen there, but of course it is not. So how do you dynamically reshuffle the codelets?
Well, maybe I can answer that, Esther, or you want to say something? Well,
no, you can answer it just completely.
Yeah, we are still working on that, but the main idea here is to use global workspace for that. So the idea is that we can receive some information from the global input, and then we can decide to make this connection a perennial one and move it to being a local input. So it's a kind of learning process where we receive information from the broadcast, and then we move it to a perennial one. I will give you an example that could be more easily to understand. Imagine that you like Japanese food for some situation, and then you watch in television a new restaurant, Japanese restaurant, and then you try this restaurant and you like it, and then you turn this restaurant into a kind of perennial connection, and then you start asking food for this restaurant again and again. So this same idea happens with these codelets. So I don't have a connection to a codelet. I get information from the broadcast. I become aware of a codelet that could provide some information to me, and then I create a fixed kind of connection between a codelet and a memory object using this new codelet that I just discovered by broadcast. Okay, this is just an idea, of course, but this can give you a hint on how we are planning to create these dynamic coalitions a long time.
Okay, thanks.
And also, yeah, I'm sorry, just to say that also we have two ways of working with CST. One now, like for the codelets to work as in the broad sense, that is like they run asynchronously or synchronously, depending on how you want. So we have a pub/sub now mechanism that you can synchronize everything and do in a sequence, or you can put each proc in a frequency, like the proc is the element that makes the codelet run. So they can run each other in their frequency and using this global workspace. I don't know if I gave the better explanation possible. Gudwin is the father of the thing, but the idea now is that we felt the need for the synchronized approach also. So now in CST, we have the two approaches available.
Just to complement what Esther said, at the beginning, in the old CST, all the codelets, they were driven by timers. So we could specify a timer and let's say 200 milliseconds or 300 milliseconds, and then you'll be having this time event that is happening, and each time that the timer calls the codelet processes its proc method and finishes, okay? And then this happens for all the codelets. But then we realized that, well, this is there are many times in which you don't have any change in the memory objects, the input memory object. There is no necessity for doing it over and over without some change of information. And then this is one of the results now from the hub. We created a new way of working with CST using a publish-subscribe kind of mechanism, where only when we have a change in the value of a sensor, for example, that is in a memory object, then we are going to call the proc on the codelet. So it is a way of not spoiling resources that could be important for the computational power of our system.
Okay, thanks. Thanks.
Okay, I think now we can continue with Leticia's presentation, in case there's people that will need to leave in 10 or 15 minutes, and then at the end we can also take more questions for Ricardo and Esther. Leticia, go ahead.
By the way, Ricardo, I wait for the address of the Japanese restaurant.
Can you see my screen? I'm not sure.
Yes, we see it's great. Go
okay.
On.
Just 1 minute. Okay. So, hi, I'm Letícia, and today I'll present my ongoing research that is part of my PhD. I'm going to show you a motivational-based learning system for CST. Motivations are vital for living beings, and they are responsible for essential functions like guiding behavior to attend to the most critical need at each moment, or designating the amount of energy to be used for executing the selected actions, and even learning. So this is the kind of behavior and autonomy we want for robots. We want robots to act intelligently and autonomously according to their own needs and goals over time. With this in mind, we got inspired by humans who can totally do this. We have many cognitive functions like emotions, context, priorities, internal states, and many others working together to determine each behavior that we will perform. And all of them impact our motivation. Also, each person is different, and we establish preferences throughout our life. So this is another variable that affects our motivation and makes us unique. But at the same time, this makes our decision-making more complex, because we have to balance our needs and preferences according to the context. So in this research, we aim to understand how different agents act in the same environment and how you balance decisions in choosing what we want and what we want and like, considering our needs and context. So we use the motivational-based learning system with reinforcement learning in our agent. There are several theories regarding motivation in psychology and correlated areas, but none of them is defined as the perfect and correct one. They all have their strong and weak points, but we choose one that seems reasonable and appropriate for initial investigations to apply to artificial creatures. In this case, we choose the drive reduction theory proposed by Hu. This theory is based on homeostasis, homeostasis concept, which is that our body works to maintain a state of balance. A drive indicates the state of arousal or tension caused by biological or physiological needs, and it motivates our organism to satisfy our needs. Also, we want to explore the satisfaction of needs according to Hugh's theory, but also the balance of needs and pleasure satisfaction. So we divided our experiments considering the dichotomy of wanting and liking relate to the motivational mechanism. Just to explain, the want phenomenon occurs in the present, but it relates to the future when the desire will be satisfied. So I can establish a goal. For example, I'm thirsty and I want to drink to relieve this need. So want is related to needs over time. And the liking phenomenon is associated with the present, and it is a subjective evaluation of a sensation. For example, I drank coffee and I like it, so it's related to the object. Here it's our proposal for a computational modeling. We designed two reinforcement learning systems, the wanting mechanism and the wanting plus liking mechanism. Following Hugh's theory, with the wanting mechanism, that is this first one, uses the current derived arousal level as part of the robot state space representation. And so reducing the drive in the direction of homeostasis will result in reinforcement signals that drive in the learning process. So the function of this mechanism is the agent has a sensor that senses a specific feature. For each sensor, we have one or more needs associated, and each one measuring the value of intensity corresponding to it, and modify the arousal level in the related drives. That is, given the drive, the agent calculates the expected reward when performing each action to choose the one that will maximize its gain. So the resulting action indicates the kind of behavior that works better in the situation. And here we have the wanting plus liking mechanism, which has two paths. The wanting, which is precisely Hugh's theory, and the liking that is related to pleasure. So the want path works the same as this first one, that is just the want mechanism. And the liking path corresponds to the hedonic dimension, that is this subjective evaluation of sensations associated with an object or an event, and it is unrelated to need satisfaction. So in this case, the agent learns directly from sensor to reward without the drive path. In our research, each object available in the environment has a fixed value simulating the agent's preferences. Just to sum up, in the wanting mechanism, the motivation comes exclusively from drive reduction. And in the wanting plus liking mechanism, it comes from drive reduction plus the pleasure or the hedonic value expected rewards. So consider all of this, we set up a series of experiments to study how distinct agents act in the same environment, how the environment's dynamic impacts the agent behavior, and how learning occurs considering different motivational mechanisms. So concerning the environment, we created two simulated environments equal in size and equipped with 4 recharge stations that I will show the next slides. The positions of these stations are the same in both environments. The only difference between them is the value associated with each station. All the recharge stations provide the same value in their same recharge environment, and each station gives a unique value in the different recharge environment. About the agents, we simulated a battery sensor ranging from 0 to 50. Then the only need our agent had was getting energy, which is related to the survival drive. We established energy equals to 30 as homeostasis because we want to simulate what happens when above or below the ideal state. And bringing this idea to the human being is equivalent to simulating when you are hungry that is below homeostasis, or eat more than necessary, that will result in above homeostasis. And we simulated 3 similar agents with the same homeostasis level, but distinguished in the energy consumption per time step, which we call it metabolism. So in the slow metabolism, the energy decay is 0.1 per time step. The normal is 1 per time step, sorry. And in the fast metabolism is 3 per time step. So we have this cognitive architecture for all agents using CST concepts. And the entire cognitive cycle comprises sensory perception, decision-making, behavioral, and motor correlates. Speaking specifically about each one, our cognitive cycle starts with the agent obtaining the data from the environment by the sensory correlates. And our agents have the battery sensor responsible for detecting the agent's energy level, the self-localization acting like a GPS, and the positions of all recharge areas. The next steps to process the data in the perceptual correlates. We have the derived survive computer responsible for calculating the difference between current energy and homeostasis. Just to illustrate how it works, we have here in this first image our battery sensor with the indication of the homeostasis point. And here we have the associated drive computation. So as you can see, when the orbit is in homeostasis, the drive value is 0 because it's just the difference. When above the homeostasis, the values are positive, and below the values are negative. So this valence distinction is crucial because we use this to detect if the agent is hungry or full in our decision making. So the next step is the agent's cognitive cycle is decision making. And here we implemented a key learning algorithm with a function approximator, and it's where the reward computations occurs according to wanting and liking mechanisms. And give the best action decided in the decision making. We have here the behavioral correlates responsible for implements each one. And finally, the motor correlate, which interacts with the environment. So this is the theoretical part. So now let's go to the fun part, that is the results. So here we have the 2 environments that I said. As we can see, they are similar, and the difference is only in the values of each energy station. In the first picture, all the stations give the same recharge value. And in the second one, each recharge has a specific value associated with it. And now some results. Just to make it easier, because I know it has been lots of information, we have here the settings of each environment, so you can use to understand what is happening. At the first look, we can already see that the behavior is very different for each agent. So considering first the same recharge environment, that is this first row, the slow metabolism, this first picture, the agent stays close to station A, that is this one, and a bit in station C, that is here. For the agent, it's not important to keep inside the recharge area because its energy decay is very slow, and the amount of recharge received is huge for its needs. So this agent prefers to explore the environment and stays close to a station when necessary. But we see a different strategy for the normal metabolism. The agent stays inside or close any station, and this agent visits more all stations than the slow metabolism agent. So we call it normal metabolism. The agent explores the environment more, but remains longer in stations. And it's interesting because in the fast metabolism, the strategy is very different because here the agent behavior is stay inside any station and not close or exploring the environment. What is expected? Because this agent consumes much energy per time step, so it can go away from recharge areas. And now, if we consider the different recharge areas, where all stations have specific values that is related to this environment, consider the three agents, we can see that all of them stay more time in station that gives the best value according to their needs. So slow metabolism focus on staying in station A, that recharges 1 in energy, and it is the lowest value, but it's enough for this agent. In normal metabolism, the focus is on staying in station D, that is this one, that recharges 2 in battery. And in fast metabolism agents, the strategy is to stay in station B, that is the one with the greater value in battery. So therefore, these experiments show that each agent acts according to what is better for their needs. When the environment allows choosing the best strategy to their conditions, they can learn how to adapt themselves and take advantage of the environment. So, okay, we saw that the wanting mechanism works very well and that the agent can learn appropriate behaviors based on its needs. But in the second part of our research, we add the liking path to the motivational mechanism. We use exactly the same environments as previous experiments with the same settings, but now we add the hedonic values for each station, and they are the same for both experiments. But each station has a specific value associated with displeasure to simulate different objects in real life. So the first number, in each station corresponds to the recharge value, and the second corresponds to the hedonic value. And now the results. Considering again the same recharge value environment, the first row, the slow metabolism focuses on station that gives the best pleasure, that this one is 4 in pleasure, the greater value. Then the normal metabolism agent prioritizes stations with higher pleasure values. So both slow metabolism and normal metabolism made choices based on maximizing the pleasure and not necessarily the need. But the fast metabolism agent does give importance to pleasure, probably because recharging for living is much more important than having pleasure. But now, considering the different recharge environment, we can first see that the robot balances better wanting and liking when it has the possibility. So the slow metabolism agent frequents the station with the lower recharge value, prioritizes the want mechanism and its needs, that is the station A, and the station with the greater pleasure, prioritizing the like mechanism, that is this one. So now it has the opportunity to balance better between wanting and liking, and it learns perfectly how to do this. With the normal metabolism agent, the behavior is similar, and it chooses the stations that give the best average recharge value and pleasure for its needs. So you can see that's okay. And on the other hand, this strategy is different for the fast metabolism agent. And in this case, pleasure is not essential as recharge. So it learns to go to the station with the more excellent, bigger recharge value. So therefore, adding liking to the motivation mechanism shows that the agents learn how to balance the gains of wanting and liking, or in other words, needs and pleasure. So finally, as conclusions of this study, we have that each agent learns how to act according to its needs, considering what is better for its metabolism. We observe the learning of all agents. The fast metabolism ones learn faster than the slow metabolism. And also we observe that the environment's dynamic impacts a lot in agents learning process and strategies. So having environments that allow the agent to adapt better for its needs is advantageous. And considering the wanting and liking motivational mechanisms, we conclude that the agents learn to balance their needs and pleasure according to their context over time. And as future works, we plan to execute these experiments using more complex environments, like non-deterministic ones. And we want to simulate agents with different levels of homeostasis. Also, we want to add more needs and drives to study how the balance between satisfying all of them occurs. We want to evaluate the decision-making and learning using these two motivational mechanisms in challenging situations, like, for example, having obstacles to reach the stations, one or more stations closed for some time, or even is being used for another agent. And finally, we know that emotions significantly impact motivation. So we plan to integrate our motivational system with the emotional architecture we are developing. So thank you all for the attention.
Thank you very much, Letícia. That was a very, very nice presentation. And please keep me updated when you start working on the emotions aspect, because I'm super interested to see how that will progress. So while people are gathering their thoughts and coming up with the questions. Oh, okay, no, we already have a question. So there's Lorraine. Lorraine, you can go ahead and unmute, and if you like, also turn on the camera.
Right. Hi. So thank you. It was indeed very interesting. I have a question concerning the exploration. What was the drive, the need for exploration? Because I was surprised in the slow metabolism ones, without the pleasure, just the needs. Why they were not exploring more and maybe using recharge, maybe the one that has a 4 points recharge, and therefore they could explore more around instead of staying around the 1 recharge and explore just around this thing.
Specifically for the slow metabolism, I would say, or? Yeah,
because this one, it doesn't lose so much energy. But it still goes to the very little recharge. It could go to the big recharge and to explore more, but it doesn't explore so much more than the others that lose energy faster.
The slow metabolism explores the environment, but they don't see urge to recharge. But considering the environment who has a specific values, the slow metabolism goes to the lowest one and they explore, but I don't show you the reward computations, but the best reward is when the agent is in homeostasis. So if they recharge a lot, they will go further the homeostasis, and it's not great. So they prefer to doesn't recharge a lot and goes to homeostasis values. So spend the energy exploring the environment and just recharge when it is necessary.
Okay, so going over the homeostasis was also not very good.
Yeah. I think that was something that I wanted to complement the information, or is that because we've created our our reward function in such a way that if you go above, it's not as bad as go below, because you're not going to die of starvation. But if you are too full, your sense of well-being is not as good as when you were okay in homeostasis. So I think it's half of the points that it loses from being away in the bottom is what we lose in the top. So the strategy, if you see, because I think Letícia didn't show this graph, but we have a graph where we run like 50 runs of the learned agent, and we try to see by starting it in different positions, what is the strategy, the mean strategy. And the mean strategy is to stay close to homeostasis. So it's different from one agent to the other, because if you have like a very fast metabolism and you need like in 3 steps, you would lose all your energy. So stay inside the battery station, because it's the only thing that we can do, the recharge station. But if you have a slow metabolism, this agent can go around, and then spend a lot of energy, and then goes to a station and gets, for instance, 1 of energy, and then it decides to go around as well, and then spend the energy again, so to be around like the homeostatic level. So that's a kind of the strategy that is learned. But one other thing that Letícia didn't mention, that was one of the most interesting results, was that the more complicated strategy to learn was for the slow metabolism agent, because it has so many options, and there are so many different strategies that you can choose, that it's easier for the other agents. We are using a reinforcement learning mechanism, but it's easier for the others that don't have these many options to survive well, to find a strategy. So is the one that is hardest to learn is the one with the slow metabolism. So that was something interesting in these results as well.
So this is also the reason why for the fast metabolism, the 2 situations are very similar. The results in the fast metabolism with the want mechanism and with the want and the liking mechanism are not very different.
No, because when they go, I think one thing that Letícia didn't mention is that when they go up, 50 is our top, it's our maximum value. After that, we have analyzing situation in the environment, because the agent doesn't see above 50 in its battery level. So if you keep recharging there and keep recharging, the agent is not going to see this, is because it's saturated. It doesn't see above that. So in the end, the strategies, they got close because of the saturation level.
Okay. I mean, what about a system where you only have the liking? You know, you like very much to go to the Japanese restaurant that Ricardo was mentioning before. How does it go? Is it going in the same way as just with the drive, or? I mean, I was wondering if you can come up with some kind of eating disorder.
I don't know, because I didn't execute this experiment, but I think the agent will choose just the best option, just the one that it likes more. I don't know.
I don't know, Ricardo, if you want to complement something, but
I think it's a good idea to try this. Maybe we can make these experiments and see what happens.
I'm very interested to see how it's going to happen when we put more agents in the scene, and then decide what competition will look like in this environment, because now it's a single agent living in Mars, but it's going to be very interesting when we do some social interaction between these agents in the environment as well.
Ale, go ahead.
I have a follow-up question on the liking, I would say. So if I understood well, the moment the preferences are preset, are predefined by the programmer, let's say. I was wondering whether you have, you are theorizing, have you considered ways for which this different preference can be, learned or acquired over time by the agent?
Good. I think you can explain better.
I think that is our primary idea, is that we decided to work with two ways. Is that first we put like, let's imagine that we inherit some preferences, that our body knows like in a biological way that chocolate is better than lettuce. Somehow with evolution, we assume that there are some bootstrap information around it. But the idea is that this information is also learned. So our evolving mechanism will be, I think that's one of our great discussions with like Ricardo and our group, is that how we can evolve this in such a way that we are not just inheriting these preferences, but we are learning them with time. And the idea is that probably the motivation itself, like the want mechanism associated with the needs, is probably mediating this like as well, but is I think that is dependable also on a broader information. So I think this long-term decision is going to change these preferences. And our idea in the future work is to investigate how we can change this these preferences by learning them with the agent in time. So I think that's the whole idea behind this mechanism. We started with like a bootstrap, but now we want to see how we can evolve that.
And I think that one interesting question is, in nature, which mechanism evolved first? We have two hypotheses. We can think that, okay, the wanting mechanism appeared first, or the liking mechanism appeared first. And it's difficult to give a solution to this, but I would guess, it's just a hint, that at the beginning we might have had just the wanting mechanisms, and but the computation of the delta drive, delta time, in some sense, it's costly, because you need to first see what happens, and then you need to go back and make a correction on that. So it's painful to learn like that. But if we can embed the liking mechanism on that, and then you can pass the like mechanism by your progeny, then in an evolutionary point of view, your children will be benefiting from having this liking mechanism without the burden to having to compute the delta drive, delta time every time, and learning everything again, because you already is capacitated by your genes to have the liking mechanism. So this is obviously a hypothesis, but I will guess that in nature, maybe the wanting mechanism appeared first, and then the liking mechanisms appeared as a kind of improvement that natural evolution brought to us in order to be faster in the computation of these reinforcements. But of course, that this is just a hypothesis.
Maybe not only faster, but smarter.
Yeah.
You know, these expensive tissue hypothesis, where people measure, compared, you know, with the same metabolism, let's say the size of the brain was, the increase of the size of the brain was balanced by a decrease in the size of the guts, you know, the stomach and that. So this, I think it goes in the direction you are saying. You know, first you satisfy what you need, but then to get smarter, you need to add something more, which is, you know, the taste or whatever it is that it goes with the liking. Yeah, so yeah, it's interesting, yes.
Well, I mean, even there, I mean, I would argue that it's tied in still biologically. So it's not just with the higher level of consciousness of what we say we like, but also there is the concept of the endocrine system that still is kind of connected. What Esther was saying before for the example of chocolate, yes, we also have the mental aspect of really liking it, but there is also just the very biological thing of how sugar and the combination of other components in chocolate influence, like your dopamine, your serotonin. I'm terrible at biology, it's obvious, so I don't know which of the two. I think it was serotonin that's like spikes after chocolate, but that one also, in addition, I think modulates this liking need. So.
And it's interesting that this also is connected to the epidemic of obesity that we have nowadays, because we didn't have the evolutionary time to adapt ourselves to a situation where we can have food everywhere and calories everywhere. And this is one of the reasons that we have this epidemic of obesity in the world right now, because in an evolutionary point of view, we didn't have the opportunity of learning from in the terms of liking, that I should not like chocolate, or I should not like food with a lot of calories, or things like that, because in the past it was necessary for survival, but nowadays maybe it is turning us into obese people.
Yeah, also the fact of being everywhere readily available and the massive overproduction of it is contributing. Is the talk of why homeostasis is the ideal, whereas overfeeding on a certain is still bad. There is also Marco that has a question. Go ahead, and I will ask you to unmute, and if you want to turn on the camera.
Yep, hi, sorry for the camera, but my computer has none. But imagine me standing here and uploading you, so thank you. A very quick question. In terms of going back to the wanting versus liking and the emergence of the liking mechanism, you said that the computed delta drive over delta time is time expanding. Might there also be a question of expanding resources, like energy resources, for computing that delta drive? So actually having all the wanting mechanism is expanding more resources for computing the learning coming from the wanting mechanism, instead of just going to the, let's say, direct route of the liking mechanism, in which we don't have to compute that. And so might also be an emergence, so emerging because of that lesser energy required for the learning process.
I think that when I say costful, maybe it's not costful in terms of computation, but in terms of time, because I need to expend time to do something, to see what happens, and then I need to use the feedback from I saw, and this costs time. And imagine that you need to learn everything that you are doing based on this kind of mechanism, that you need to first do something and see the consequences of it. But instead, the liking mechanism can give me this as a bonus, because I don't need to make those experiments in the world and see the result of it. I don't think that these cost is too hard in terms of computational power and making but the problem is time. I don't have in my life enough time for trying everything, and if my liking mechanism, my feelings can give a hint on that, this can I know that fruits are good because I taste them and they taste good. I don't need to eat a fruit and see if it's going to feed me, and then I need to move to a different fruit. You see, so the real problem in terms of cost here is time and not computational power.
And I think is that it's time, along with the fact that Letícia experimented, they were like with only one drive and one one percept that you would like. But if you broaden that, if you think that we have many drives, and these drives, they get more complex and more complex as we evolve, because like you have very simple ones at the beginning, but probably you're going to get a much more complicated drive set. The result of your action is going to affect, and your what you pick is going to affect differently many drives. And then to assess in the end your long time decision making process and see, actually, what was the, what impacted this decision in the end? Like how these differences in each drive, in each element contributed to the reward itself and everything. So this is very consuming because you need a lot of experience, as Ricardo said, to disentangle this information and to see actually what is the one that is providing the reward itself. So, and another thing that is interesting is that I think that Letícia didn't put a lot of focus on that, but is that the way that we are trying to model this relation with want and drive in the cognitive agent is that when you have a percept in memory, you have a like associated to that, but the want depends on the drive itself. So the like comes together with the percept and is independent of anything else that is happening. So I ate chocolate, and the like associated to chocolate is there. So if I have a decision-making mechanism that can put everything that is available on the table, and I could just look to the like, consider that we don't have needs, but you could just look to your preferences. There is a very quick decision making because you just maximize if this is the only thing that you can use, you just take the one that that gives you the best reward possible, the best return possible. So it's a very quick decision making process, or at least that you can, if you have a draw, it's really easy to say, okay, in the sense that everything is possible, I would pick the thing that I like the best. And our experiments were in this direction to see if I don't have a need, the agent can pick what it likes best. But if in the presence of need, if both align, I eat chocolate. Otherwise, I would eat lettuce because I am so hungry and I need something that it doesn't matter. I do like lettuce, by the way, but I eat lettuce because it's the only thing that is available for me. So that's something that we wanted to show with this dual mechanism, that when it's aligned, it's perfect, but when it's not, the need goes in place because it's a kind of survival thing. So, and as this get more complicated, we see how it's going to happen, because now we are going to put like mechanisms that will be competing between themselves, and we see how this agent is going to evolve. But it's interesting. I think Julio mentioned some experiment that we want to do, but we change the metabolism just to say, okay, if everything is equal, but we just, if I take the same structure of an agent and I want to create different agents, I just need to change one variable and everything else will be different. Everything is, so if you need like different agents in your environment, you just have to change a small variable there. And this variable is sufficient to have very different behavior, even in the face of the same experiences, even in the face of the same mechanism behind it. Just one variable is sufficient for us to have a very different set of agents in the environment. And that's really nice to watch. So I think explains a lot of us, like as we behave, because like we face the same experiences, but we raise two kids in the same environment and they end up completely different because they have biological mechanisms and embodiments that are different. So, and that's what we are trying to show.
Yeah, well, on this line, I guess I suspect that we have just one drive and many likes. Don't you think so? I mean, because on some sense, you know, the drive is just, well, it's just within brackets survival, no? While the likes, you may like chocolate, but you may like something else, or so this maybe the system is unbalanced toward the likes, at least it seems to me. And knowing how, for example, Alessandra likes chocolate very much, you know, she would do anything to eat chocolate. The other thing I want to say is that in general, you may also, maybe somebody else already mentioned it, but maybe in some sense you also need to take into consideration the cost of learning how to reach food, you know, because if you like chocolate, I mean, you may need to know how to find chocolate, and this requires some effort in terms of reasoning, and so the cost of learning how to find food maybe should also be taken into consideration. Besides, it may be too difficult to find, or it may be that it's not as good metabolistically, but it's easier to find. So maybe this is another parameter that may be interesting to consider.
It's interesting because this is something that it's in our radar, but we didn't have the time yet to go after it, because besides Hull's theory of drives, we also have a theory of impulse. So the idea is that instead of have a permanent drive that is driving our behavior, we might have impulses that are related to the affordances that the different objects that we recognize in the environment affords to me. So if I don't see a chocolate, probably I will not feel the urge to go after the chocolate. But if the chocolate is in front of me, the affordance of the eatability of the chocolate will force me to pick the chocolate and eat it. And so if we insert this idea of an impulse in the mechanism, maybe we can have more interesting kinds of mechanisms. But in the work of Letícia, we started to start with the very beginning of Hull's theory of drives, but we know that we will be making it more complex with time, and maybe we'll need to introduce the impulses theory in the experiments.
It was not a criticism for Letícia. She's doing a very nice job.
Yeah, of course.
Yeah, I think that this impulse can also help. If not, it can be the way to ease the process. It's not that I'm not going to think about chocolate, even if it's not present. Probably there are some other mechanisms that
memory.
Yeah, no, but
I will remember.
No, it will remember, probably because if you like a lot, there is a high chance that you're going to recall this information, even if you're not seeing. But the impulse and the affordances that are available, what you are seeing in the environment, are probably be easing up the other elements. So it's going to be a very interesting competing mechanism as well, because you have what is available and you have what you do like. This is something like probably related to addiction. That is some interesting study in this direction of addiction, because you can see like it's not in the scene, but I'm thinking constantly on that, and I need that, and I drive for this kind of thing. So that's something that we will like. I think Letícia's work is going to open like 10 different works for us in the group, because there are plenty of interesting stuff that we want to do. But the impulse one it's already written down. It's not implemented, but it's written down in our work already here.
And I believe that also another interesting thing that we could include into this kind of motivation discussion is the notion of duty. I have to do something because it's my duty. So in some situations, I don't like doing something, but I do that because I feel that I have to do that, you see. So then in some sense, it's the same kind of dimension that we have in terms of liking, but is in a higher level, because now we are talking about things that motivates us to be done, but are not exactly related to pleasure, but to a higher level kind of instinct that is duty. Okay? So it's also an interesting complexification that we can put into the experiments.
Yeah, I mean, even Maslow had like duty and all of the higher moral, let's say, obligations,
Yeah.
they come
Yeah.
after drives. They come after drives and even after the wants. It's once these are
Depending on the
satisfied.
person, you see, because some people will put them in a first priority, but other people you do the opposite. Okay, I do what I want, and then I like, I don't bother with moral things, and you see.
Yeah,
Very
there
true.
is there is something that we are like we are very curious in how this drive mechanism evolves. Do we start are we Freudian and we start with just 2 dimensions of drives, and then as we model these drives as vectors of real values in our system, in our computational system, but we think that it might be the case that the drives evolve as we reuse some decision making, as we do some things to solve this drive, and this set of actions, they are the ones that you use to drive. As we do this, we create subdrives and subdrives, and subdrives are actually trying to achieve specific levels of these basic drives. So if you can say that social, the moral part or the social part is related to very specific values that we've learned to attend in terms of these drives, it might be an interesting hypothesis to see how we create the Maslow pyramid by evolving these from two simple dimensions, just trying to create new drives to answer to these small subgroups of values that we have. That's something that we also are going to investigate. We are trying to investigate in the group.
All right. Well, I think this was a very, very nice discussion to develop. If no one has any follow-up questions, I think we can wrap up the event here. So please join me in thanking our speakers that did a great job. All of the virtual applause for now. And the recording of this talk will be uploaded shortly, either within today or tomorrow on our channel. And I can paste you here in the group the link for the people from second. There we go. So here is where we track all of our events. Usually after the event has passed, you will have there the link to the recording plus everything. And at the top of the page, there is also the link to subscribe to the mailing list. So if you want to be kept up to date with the upcoming events, that's where to go. Thank you very much. I hope you have a lovely day there in Brazil. A wonderful afternoon to everyone here in Europe, and see you for the next ICOG event. Bye-bye.
Thank you all. Bye-bye.
Thank you.
Thank you.